What if the solutions to some of our biggest modern challenges were hidden in plain sight, buried in the forgotten blueprints of medieval engineers? Picture this: centuries before skyscrapers or smartphones, ancient builders were crafting structures so advanced they rivaled today's cutting-edge technology. And here's the twist: they had no idea they were solving problems that wouldn't even exist for hundreds of years. From water systems that purified without chemicals to buildings that swayed with earthquakes like modern shock absorbers, these unsung innovators left behind a treasure trove of accidental genius. Think about the last time you turned on a faucet or walked into a sturdy high-rise. We take these conveniences for granted, assuming they're purely modern triumphs. But what if I told you that medieval engineers had already cracked the code? They worked without computers, without advanced materials, often without even understanding the science behind their own creations, yet their designs were so precise, so forward-thinking, that today's experts still study them in awe. These weren't just lucky guesses, they were glimpses of human brilliance transcending time. So how did they do it? That's the mystery we're about to unravel. Over the next 25 revelations, we'll travel back to an era where intuition and raw ingenuity built wonders that still leave us speechless. You'll see how a 13th century cathedral holds secrets to earthquake survival, how a 1,000-year-old filter system outsmarts modern pollution, and why a forgotten medieval material might just revolutionize sustainable construction today. This isn't just history, it's a roadmap to the future, hidden in the past, ready to meet the accidental visionaries who shaped our world without even knowing it. Let's dive in. The Romans didn't just build aqueducts, they mastered the art of moving water with an elegance that puts modern systems to shame. Take the Aqua Claudia, stretching over 45 miles from mountain springs to the heart of Rome, all without a single pump. How pure gravity! The slope was calculated so precisely that water flowed at just the right speed, fast enough to prevent stagnation, slow enough to avoid erosion. That's a level of precision modern engineers still admire. And here's the kicker: they did it without lasers, without satellites, using nothing more than chorobates, a simple wooden level, and an intuitive grasp of physics that feels almost supernatural today. But the real genius wasn't just in the delivery, it was in the details. Settling basins along the route acted like natural filters, letting sand and debris sink to the bottom before the water continued its journey. Sound familiar? It's the same principle behind modern sedimentation tanks in water treatment plants. The Romans even used charcoal and porous clay pipes to purify water further, centuries before we understood germ theory. And let's talk durability. While today's pipes crack and corrode within decades, the Pont du Gard has stood for nearly 2,000 years, its limestone blocks still holding strong without a drop of mortar. That's not just craftsmanship, it's a lesson in choosing the right materials for the job. What's most humbling is how these ancient systems put sustainability first. No energy-guzzling pumps, no chemical additives, just a deep respect for natural forces. Modern engineers are now circling back to these ideas, using gravity-fed systems in places like New York City, where tunnels modeled after Roman aqueducts deliver water to millions. Even the concept of water audits traces back to Frontinus, Rome's water commissioner, who meticulously documented flow rates to prevent waste. It's a reminder that sometimes the most advanced solution isn't the newest one, it's the one that stood the test of time. While we marvel at today's towering wind turbines spinning silently across landscapes, their ancestors were already hard at work 800 years ago, not with electricity, but with sheer mechanical ingenuity. Medieval windmills weren't just quaint countryside features, They were power plants of their era, converting breeze into productivity with startling efficiency. Take the Dutch, who didn't just harness the wind, they used it to rewrite geography. Their iconic post mills, perched on wooden trestles, could pivot to face changing winds, maximizing energy capture centuries before modern turbines adopted the same swiveling design. But here's what's truly astonishing. These structures didn't just grind grain. They transformed entire ecosystems. By channeling wind power to turn Archimedes screws, Dutch mills drained vast swamps, turning uninhabitable marshlands into fertile fields, a medieval version of battling rising sea levels. The secret to their success, a marriage of simplicity and sophistication. Craftsmen shaped wooden sails with curved airfoils, intuitively mimicking the aerodynamics that engineers now study in wind tunnels. The weight and spacing of each sail blade were calibrated to balance torque and stability, just as turbine engineers today fine-tune composite materials for optimal lift. And durability, many mills operated daily for generations, their oak gears and axles weathering storms that would cripple modern machinery. This wasn't just brute force engineering. It was a dialogue with nature, working within its rhythms rather than against them. What's most inspiring is how these mills became community lifelines. Villages clustered around them, sharing the energy source like an early power grid. The miller wasn't just a laborer, he was the keeper of technology that fed and sustained entire regions. Fast forward to today, and the parallels are uncanny. Just as medieval towns relied on steady winds, modern cities invest in wind farms as communal energy solutions. Even the evolution of materials echoes across time. Where blacksmiths once reinforced wooden mechanisms with iron straps, today's engineers layer carbon fiber over turbine blades for strength. The lesson, sustainable energy, isn't about reinventing the wheel sometimes. It's about rediscovering the wisdom already spinning in the wind. The Pantheon's dome isn't just an architectural marvel, it's a silent rebuke to modern engineering. While today's concrete bridges and highways crumble after 50 years, this 2,000-year-old masterpiece stands flawless, its curved ceiling still the largest unreinforced concrete dome on Earth. The secret lies in a recipe so advanced, scientists only cracked its code in the last decade. Roman builders mixed volcanic ash from Pozzuoli with lime and seawater, creating a chemical reaction that forms tiny crystalline structures as strong as steel. But here's the miracle. When cracks form, rainwater reacts with leftover volcanic material to grow new minerals, sealing fractures automatically. It's not just durable, it heals itself like living tissue. Modern labs are racing to replicate this ancient alchemy. Researchers at MIT discovered that Roman concrete contains strettlingite, a mineral that blocks crack propagation by forming plate-like barriers, something modern mixes lack. Engineers now add volcanic rock or fly ash to concrete, mimicking the self-repairing properties lost for centuries. Japan even developed a bioconcrete with bacteria that produce limestone to fill gaps, inspired by Rome's accidental genius. The irony, we're spending billions to reinvent what ancient masons perfected with local ingredients and no chemistry textbooks. What's truly humbling is how this lost technology solves two modern crises at once. First, durability. Replacing just 40% of Portland cement with volcanic ash could double a structure's lifespan, reducing endless repair cycles. Second, sustainability. Traditional cement production spews 8% of global CO2 emissions, while Roman-style concrete actually absorbs carbon dioxide over time. The Pantheon's dome isn't just a relic, it's a blueprint for greener cities. From seawalls in San Francisco to nuclear waste containment, projects are now testing this ancient future material. The lesson: sometimes progress means looking backward to an era when builders thought in centuries, not quarterly reports. Perhaps the most poetic twist lies in how these discoveries unfolded. For years, scholars assumed Roman concrete's longevity came from meticulous craftsmanship. But when geologists analyzed drilling samples from ancient harbors, they found seawater had transformed the concrete into something even stronger over time, a feature modern engineers call pozzolanic activity. The very environment that destroys our structures had perfected theirs. It's a reminder that the best engineering doesn't fight nature, it collaborates with it, turning what we see as threats into allies. As climate change demands resilient infrastructure, the Pantheon whispers across millennia. The answers are here, waiting in the ashes of volcanoes and the patience of stone. Imagine a world without earthquake warnings, no sirens, no smartphone alerts, just the sudden terror of the ground shaking beneath you. Now picture this: nearly 2,000 years ago, a brilliant Chinese scientist named Zhang Heng crafted a solution so elegant, it still baffles engineers today. His bronze seismoscope didn't just detect quakes, it pointed to their epicenters with uncanny accuracy, all without a single microchip or battery. How? 8 sinuous dragons coiled around a central urn, each clutching a bronze ball in its jaws. When tremors rippled through the earth, a hidden pendulum inside would swing, triggering just one dragon to release its ball into the waiting mouth of a frog below. The direction of the fallen ball revealed where the quake had struck, sometimes hundreds of miles away. What's astonishing isn't just the mechanics, it's the philosophy behind them. Modern seismographs measure ground motion precisely, but Zhang's device prioritized something we often overlook today: immediate, actionable intelligence. In an era without radio or telegraph, his dragons gave officials a head start to dispatch aid or reinforce defenses before aftershocks hit. Records show it once detected a quake so distant, messengers arrived days later confirming what the Seismoscope had already revealed. That's not just engineering, it's foresight carved in bronze. The real stroke of genius lay in its simplicity. While modern sensors rely on delicate electronics, Zhang's design embraced the chaos it measured. The urn's heavy base absorbed minor vibrations, ensuring only significant tremors tripped the mechanism, a crude but effective filter against false alarms. Historians believe he may have used a clever system of levers and hinges, but the exact workings remain a mystery. When attempts were made to reconstruct it in 2001, engineers found the design responded to seismic waves modern devices barely registered. This wasn't just a tool, it was a statement. Ancient China's dynasties invested heavily in disaster prevention, viewing earthquakes as cosmic imbalances demanding human intervention. Zhang, an astronomer and poet, likely saw his creation as part of a larger dialogue between heaven and earth. Today, as cities from Tokyo to San Francisco deploy AI-powered alert systems, the goal remains unchanged: buying seconds that save lives. The difference: we've swapped bronze dragons for fiber optic cables, but the urgency and the ingenuity bridges centuries. Perhaps the most poignant lesson lies in what we've lost. Modern seismology maps quakes in intricate detail, yet many communities still lack basic early warning networks. Zhang's Seismoscope, funded by an emperor who valued collective safety over profit, reminds us that technology alone isn't enough. It takes vision to wield it wisely. As engineers now explore low-cost seismic solutions using smartphone sensors, they're unknowingly echoing an ancient truth: the best innovations don't just solve problems, they honor the lives behind them. In the scorching heart of Iran's deserts, where summer temperatures could melt modern air conditioners into useless husks, Persian engineers crafted a masterpiece of passive cooling: the wind catcher. These towering structures, some reaching 90 feet high, weren't just decorative. They were ancient climate control systems, harnessing the slightest breeze to transform sweltering interiors into oases of comfort. Take the city of Yazd, where wind catchers crowned every home like natural skyscrapers. Their secret, a clever interplay of physics and architecture. Each catcher's vertical shaft faced prevailing winds, funneling air downward into the building's core. But here's the genius: as hot air entered, it passed over water channels or thick clay walls' thermal mass that absorbed heat like a sponge. By the time the air reached living spaces, it had dropped 20 degrees or more, all without a single watt of electricity. What's truly remarkable is how these designs anticipated modern eco-architecture. The wind catcher's principles now inspire passive ventilation systems from London to Los Angeles. Architects studying Yazd structures discovered something astonishing. The angled openings weren't random. They were calibrated to capture even the faintest nocturnal breezes, storing coolness in the building's thermal mass to last through the day. It's the same principle behind today's tram walls and thermal labyrinths, where materials like adobe or rammed earth absorb heat by day and release coolness by night. Even the orientation was scientific. Many catchers had multiple openings to exploit seasonal wind shifts, a primitive but effective form of adaptive design. The wind catcher's legacy stretches far beyond homes. Its aerodynamic profile directly influenced the hyperbolic cooling towers of nuclear power plants, where the same stack effect pulls hot air upward with breathtaking efficiency. Contemporary engineers have taken notes too. Dubai's Masdar city incorporates modernized wind towers that reduce air conditioning needs by 40%, while universities in Arizona are testing 3D printed ceramic catchers that mimic ancient Persian geometry. The irony: we're spending millions to replicate what desert builders perfected with mud bricks and intuition. Perhaps the most profound lesson lies in the philosophy behind these structures. Where modern cooling often fights nature with brute force energy, wind catchers worked in harmony with their environment. They didn't just cool air, they purified it, with dust settling in the shaft's recesses before the breeze entered living spaces. And because they required no moving parts, many have operated flawlessly for centuries. As climate change forces a reckoning with energy-hungry technologies, these ancient towers stand as silent mentors, proving that sustainability isn't about inventing new tools, it's about rediscovering the wisdom etched in clay and wind. Nowhere is this revival more poetic than in Iran itself, where young architects are blending traditional wind catchers with solar panels, creating hybrid systems that need no grid power at all. It's a full circle moment. The same breezes that cooled civilizations millennia ago are now inspiring a greener future. The next time you feel an air conditioner's hum, remember the desert's answer to comfort wasn't found in circuits or refrigerants, but in the quiet dance between air and earth, a dance choreographed by engineers who understood that true innovation doesn't conquer nature, it converses with it. High above the roaring Apurimac River in Peru, where modern steel bridges would shudder under seismic tremors, the Inca crafted crossings that danced with the Earth's movements. Their suspension bridges, woven entirely from iku grass, weren't just feats of engineering, they were living monuments to flexibility. Picture strands of grass twisted into ropes as thick as a man's thigh, braided together to form cables strong enough to support armies and llama caravans. But here's what defies belief. These bridges had no rigid supports, no metal reinforcements. Instead, they swayed like giant hammocks, absorbing the violent shakes of earthquakes that would snap modern rigid spans. The secret: the Inca understood something we're only now prioritizing. Structures shouldn't resist nature's forces, they should move with them. This ancient wisdom echoes in today's seismic engineering. The Golden Gate Bridge's ability to flex during quakes owes much to the same principle-controlled movement dissipates energy. But while modern engineers rely on complex computer models and shock absorbers, the Inca achieved resilience through biology. Grass ropes, unlike steel, have natural give. When strained, individual fibers redistribute tension rather than breaking catastrophically. It's a lesson material scientists are now applying to carbon fiber composites and self-healing polymers. Even the bridge's annual rebuilding ritual held hidden genius. Communities would gather to weave new sections, inspecting every strand, a practice mirroring modern, planned obsolescence strategies for critical infrastructure. The difference, where we replace parts based on theoretical wear, the Incas' hands-on approach caught micro-failures before they escalated. The surviving Huachuca Bridge isn't just a tourist attraction, it's a masterclass in community-driven engineering. Each year, 4 Quechua communities spend 3 days reweaving the 400-year-old design using techniques passed down orally. No blueprints, no safety harnesses, just collective memory and shared purpose. This ritual does more than maintain a crossing. It reinforces social bonds and preserves indigenous knowledge that predates the wheel in the Andes. Modern engineers could learn from this holistic view of infrastructure, not as isolated steel and concrete, but as extensions of human networks needing constant care. What's most revolutionary is how these bridges solved problems we're still grappling with. Their lightweight design required no heavy machinery to install, leaving minimal environmental footprint, a stark contrast to today's carbon-intensive bridge construction. And because materials were locally sourced and biodegradable, decommissioned bridges simply returned to the earth without pollution. As we search for sustainable alternatives to steel and concrete, the Incas' grass bridges whisper an unexpected truth. Sometimes advanced technology looks like twisted straw and calloused hands. The real innovation wasn't just in the weaving, it was in seeing infrastructure as something alive, something that breathes with the land it binds together. Perhaps the ultimate testament to their brilliance lies in what didn't happen. While colonial stone bridges crumbled in quakes, the flexible grass spans survived until Spaniards, distrusting their primitive appearance, replaced them with rigid arches that promptly collapsed. It's a cautionary tale about dismissing traditional knowledge. Today, as engineers design bridges to withstand climate-driven superstorms and rising sea levels, they're circling back to the Incas' core insight. Resilience isn't about being unbreakable. It's about knowing how to bend. Imagine a weapon so fearsome, it could set the very sea ablaze, a liquid fire that clung to ships and flesh alike, defying all attempts to extinguish it. This was Greek fire, the Byzantine Empire's closely guarded secret that turned the tide of naval battles for centuries. While modern flamethrowers trace their roots to World War I, the Byzantines had already perfected the concept over 1,000 years earlier. Their weapon wasn't just terrifying, it was a marvel of early chemical engineering. Historians believe Greek fire combined crude petroleum with quicklime and other additives, creating a substance that ignited upon contact with water. But the real breakthrough wasn't just the fuel, it was the delivery system. Bronze siphons, heated and pressurized, could spray jets of flame over 100 feet, a shocking range for medieval technology. These weren't crude torches, they were precision instruments of war, mounted on ships' prows like the naval artillery of their day. What set Greek fire apart wasn't just its destructive power, it was the Byzantines' understanding of psychological warfare. The sight of fire dancing across waves sent enemies into panic, often scattering fleets before combat even began. Contemporary accounts describe its eerie glow illuminating night battles, the screams of sailors trapped in inextinguishable flames echoing across the water. Modern military strategists recognize this as an early example of shock and awe tactics, using overwhelming, unpredictable force to break enemy morale. The parallels to today's incendiary weapons are uncanny. From napalm in Vietnam to thermobaric bombs, the principle remains the same. Fire isn't just a tool of destruction, it's a weapon of the mind. The most fascinating aspect might be the empire's ruthless protection of the formula. Only a handful of artisans knew the full recipe, their knowledge passed down through select families under penalty of death. This wasn't just secrecy, it was medieval intellectual property protection at its most extreme. When enemies captured Greek fire supplies, they couldn't replicate it. The exact mixture and pressurization techniques remained elusive. In an era before patents, the Byzantines understood that true power lay not in the weapon itself, but in controlling the knowledge behind it. Modern corporations employ similar strategies today, guarding trade secrets from Coca-Cola's formula to silicon chip designs. The difference, where Byzantine emperors used execution as enforcement, today's companies rely on non-disclosure agreements. Recent forensic archaeology hints at why Greek fire was so unique. Analysis of residue from Byzantine naval bases suggests the mixture may have contained potassium nitrate, a key component of gunpowder. This raises a tantalizing possibility. Greek fire wasn't just an incendiary, but a primitive form of explosive. Some historians now theorize the siphons used compressed air systems similar to early steam engines, projecting the substance with terrifying force. Replicas built using these principles have produced flames matching historical descriptions, though the exact formula remains debated. What's undeniable is the weapon's lasting influence. From the flame projectors of World War II to the incendiary drones used in modern conflicts, the shadow of Greek fire stretches across centuries of warfare. Perhaps the most enduring lesson lies in its paradoxical legacy. A weapon designed to protect Constantinople ultimately couldn't prevent the empire's fall, yet the science behind it propelled human understanding of chemistry and pressure systems forward. Today's firefighters ironically benefit from this ancient weapon's principles, using similar pressurized systems to combat blazes instead of spreading them. The story of Greek fire reminds us that even the most destructive innovations can spark unintended progress, their embers glowing long after the battles they fought fade into history. In the end, the flames died out, but the ideas behind them kept burning, illuminating paths to technologies we're still discovering today. Standing over 100 feet tall and weighing as much as 50 elephants, the obelisks of ancient Egypt weren't just monuments, they were gravity-defying puzzles carved from a single block of stone. How do you move a 100-ton needle of granite across miles of desert without cranes or trucks? The answer lies in a blend of physics and patience that would make modern engineers blush. Workers would first carve trenches around the obelisk's base, then slide wooden sledges beneath it. But here's the stroke of genius. They'd wet the sand in front of the sledge, reducing friction by up to 50%. Recent experiments show this technique allowed just a few dozen workers to drag blocks that would otherwise require hundreds. A lesson in lubrication we've only recently quantified with modern tribology. The same principle now inspires engineers moving mega-telescope components across Antarctic ice or positioning offshore wind turbine foundations. Precision didn't end with transportation. When raising an obelisk, Egyptians used a system of ramps, counterweights, and pivots so exact, many still stand perfectly vertical after 3,000 years. Compare that to modern skyscrapers, which often lean centimeters within decades. But the real magic happened during alignment. Temple obelisks were positioned to cast shadows marking solstices and equinoxes, their tips aligning with celestial events to within fractions of a degree. Today, we'd need GPS and laser theodolites to achieve such accuracy. They did it by tracking the sun's arc with nothing but shadows and mathematics. The Temple of Karnak's axis, for instance, aligns so precisely with the winter solstice sunrise that even now, the sun's first rays slip through its gates like a key turning in a lock. The unfinished obelisk in Aswan's quarries is perhaps the most revealing artifact of all. Left cracked in its bedrock, this abandoned giant shows the Egyptians' methodical approach to problem solving. Chisel marks reveal how workers carved downward in trenches, leaving the obelisk attached at its base until the final moment, a fail-safe against fractures. Nearby, archaeologists found dolerite pounding stones, each worn smooth from years of patient hammering. This wasn't brute force, it was controlled percussion, with workers systematically weakening crystalline structures along fracture lines. Modern diamond wire saws used in quarries operate on the same principle of targeted stress, just with motors instead of muscle. What's most humbling is how these feats reflect a culture that thought in centuries, not fiscal quarters. Where we might calculate a building's lifespan in decades, obelisks were engineered for eternity. Their tapered shape isn't just aesthetic, it's structurally optimal, distributing wind loads and thermal stresses evenly. The capstones sheathed in electrum weren't merely decorative, they acted as lightning rods, dissipating strikes that could shatter lesser stones. Even the hieroglyphs served a purpose. Carved symmetrically, they helped balance thermal expansion across the monument's faces. Nowhere is this legacy more alive than in contemporary megaprojects. When engineers transported NAS, a space shuttle Endeavour, through Los Angeles streets in 2012, they used a custom-built dolly not unlike Egyptian sledges. The Burj Khalifa's foundation employs load distribution techniques eerily similar to those in Luxor's temples. And when precision matters most, like aligning particle accelerators or radio telescopes, we still look to the stars, just as the ancients did. The difference: they had no margin for error, no software to correct mistakes. Their measuring tools were the heavens themselves, their blueprints written in sunlight and shadow. Perhaps the ultimate testament to their skill lies in what didn't happen. Despite moving hundreds of obelisks across centuries, archaeologists have found no evidence of catastrophic collapses during transport or erection. Each success was the result of painstaking trial and error, knowledge passed down through generations of artisans. In an age obsessed with disruption, the obelisks whisper a counterintuitive truth: sometimes the most radical innovation is perfecting the basics. As we face our own engineering challenges, from relocating historic buildings to constructing lunar bases, we're rediscovering that the gap between ancient and modern isn't as wide as we thought. The tools have changed, but the laws of physics haven't, and neither has human ingenuity's ability to bend them to our will. Deep in the jungles of Tikal, where modern cities would drill wells or pipe water from distant sources, the Maya engineered a solution so elegant, it puts today's water crises in stark relief. Their sprawling metropolis thrived in a region with just 2 seasons torrential rains, followed by months of drought, yet they supported populations rivaling medieval London without rivers or lakes nearby. The secret: a network of reservoirs so sophisticated, they functioned like ancient versions of modern water treatment plants. At the heart of their system lay the Temple Reservoir, a man-made basin lined with volcanic ash and crushed limestone. This wasn't just storage, it was chemistry in action. As rainwater filtered through these layers, impurities bonded with the minerals, leaving behind cleaner water. Sound familiar? It's the same adsorption principle used in today's activated charcoal filters, just without the plastic cartridges. But the Maya didn't stop at passive filtration. They engineered entire landscapes to maximize water capture. plazas weren't just ceremonial spaces, they're carefully calculated slopes channeled rainwater into canals with millimeter-perfect gradients. Archaeologists using laser mapping recently discovered these surfaces tilted at precisely 1 degree, enough to prevent stagnation yet gentle enough to avoid erosion. Even the famous stepped pyramids played a role, their stucco coatings acting as catchment areas funneling water into underground cisterns. Modern cities from Singapore to Los Angeles now employ similar sponge city designs, using permeable pavements and green roofs to mimic this ancient hydrology. The difference: where Maya engineers shaped limestone, we pour concrete, but the goal remains unchanged. Every drop counts. What's most revolutionary about their system was its resilience. During prolonged droughts, some lasting decades, the Maya didn't just survive, they adapted. Sediment cores reveal fascinating adjustments. When water levels dropped, they introduced aquatic plants like water lilies. These weren't merely decorative, their roots oxygenated the water and hosted microorganisms that broke down waste, creating a self-sustaining ecosystem. Today's constructed wetlands for wastewater treatment operate on the same biological principles. Even their famed hieroglyphs held hydrological wisdom, recording rainfall patterns and reservoir levels with a precision that modern climatologists use to reconstruct ancient weather cycles. The real lesson lies in how holistically the Maya viewed water. Where modern systems often separate drinking supply, sewage, and stormwater into disconnected networks, their approach was integrated. Residential compounds had their own small-scale filtration systems, with layered gravel beds that purified greywater for irrigation. The largest reservoirs even featured diversion channels to manage overflow during hurricanes, a primitive but effective form of flood control. As California and Australia battle worsening droughts, engineers are looking back at these techniques. Projects like the Tikal Initiative now test whether blending ancient reservoir designs with modern materials could create drought-proof water systems for vulnerable communities. Perhaps the most poignant discovery came from the Maya's collapse. Pollen samples show that as their society declined, water quality deteriorated, not from lack of technology, but from deforestation and siltation. The very reservoirs that sustained them for centuries became breeding grounds for algae and disease when surrounding ecosystems were disrupted. It's a warning etched in limestone. No engineering, no matter how brilliant, can compensate for broken ecological balances. As climate change intensifies, the Maya's legacy offers both inspiration and caution, proof that civilizations can flourish in harsh environments, but only when they listen to the land's rhythms and respect the delicate dance between human need and natural limits. While modern industrial farms pump synthetic nitrogen into depleted soils, medieval farmers across Europe were perfecting a system that kept their lands fertile for generations without a single chemical in sight. The three-field rotation wasn't just clever, it was revolutionary. By dividing fields into thirds, one for winter crops like wheat, one for spring crops like peas or oats, and one left fallow to rest, they created a self-sustaining cycle that industrial agriculture would later ignore at its peril. Here's the brilliance: each crop played a specific role. Legumes planted in spring naturally fixed nitrogen in the soil, a process scientists wouldn't understand until the 19th century. The fallow field wasn't wasted, it grazed livestock whose manure became next year's fertilizer. This wasn't farming, it was alchemy, turning time and biodiversity into abundance. What's astonishing is how this system anticipated modern agroecology. Researchers analyzing medieval crop yields found soil organic matter levels rivaling those in today's best organic farms. The secret: diversity. Where monocultures invite pests and deplete nutrients, rotating crops disrupted disease cycles and replenished the earth. A 12th century farmer might not have known about rhizobacteria or nutrient cycling, but their fields thrived on these invisible partnerships. Fast forward to today and the parallels are striking. The green manure techniques used in regenerative agriculture, planting clover or vetch to enrich soil, are direct descendants of medieval practices. Even the rise of cover cropping, now hailed as a climate solution, mirrors the fallow fields of the past, just with science-backed precision. But the real masterstroke was how this system nourished communities, not just soil. Winter grains provided bread, spring crops delivered protein-rich peas and lentils, while livestock supplied meat and dairy. This wasn't just crop rotation, it was dietary rotation, ensuring balanced nutrition centuries before vitamins were discovered. Records from English manor houses reveal peasant diets often outperformed those of later industrial workers in protein and micronutrients. The lesson: sustainability isn't just about the land, it's about the people it feeds. Modern studies confirm this. Diverse rotations increase yields by up to 20% compared to monocultures, while reducing pesticide use. The medieval world didn't just farm smarter, it ate better. Perhaps the most poignant twist lies in why we abandoned this wisdom. The allure of synthetic fertilizers in the 19th century promised shortcut abundance, but at a cost. Today, with topsoil eroding 10 times faster than it forms and dead zones spreading in oceans from fertilizer runoff, we're relearning what medieval farmers knew instinctively: you can't cheat ecology. Pioneers like Elliot Coleman, whose organic methods feed thousands year-round in Maine winters, openly credit the three-field system as inspiration. Even NASA, planning future Martian colonies, studies these rotations for closed-loop food systems. The irony: the old ways are now cutting edge. The ultimate testament to this system's genius isn't in history books, it's in the ground. Archaeologists excavating medieval sites often find darker, richer soil layers marking these farming eras, starkly contrasting with degraded soils from industrial periods. As climate change forces a reckoning with unsustainable agriculture, the past offers a path forward. From the terraces of Peru to the rice paddies of China, ancient farmers worldwide developed similar principles independently. Their shared insight: true productivity doesn't strip the land, it dances with it season after season, in a rhythm as old as dirt and as vital as tomorrow's bread. Rome didn't just build roads, they engineered a transportation network so advanced, modern highway systems still borrow from its blueprint. Picture this: beneath the cobblestones of the Appian Way lies a cross-section of engineering genius. First, a trench dug deep enough to reach stable subsoil. Then, layers of crushed stone, gravel, and sand meticulously compacted to distribute weight evenly, a technique identical to today's roadbed construction. But the Romans didn't stop there. The crowning layer, tightly fitted volcanic rock slabs, angled slightly outward in a cambered design that shed rainwater like a duck's back. This wasn't just durability, it was hydrodynamics in stone. 2,000 years later, stretches of these roads still survive, while modern asphalt cracks under decades of use. What's truly groundbreaking is how these roads functioned as an ancient internet. Relay stations dotted every 10 miles, where fresh horses and riders stood ready to carry messages at breakneck speed. Imperial couriers could cover up to 150 miles a day faster than the Pony Express. The roads weren't just paths, they were information superhighways, binding the empire together with a speed unmatched until railroads. Modern logistics companies unknowingly echo this system. Amazon's distribution hubs and FedEx's air routes follow the same hub and spoke model Rome perfected. Even the Roman milestone, marking distances to the capital, finds its descendant in today's highway exit signs. the secret sauce, standardization. Roman engineers enforced strict construction codes across provinces. Wheel ruts were spaced consistently to match cart axles, an ancient version of railway gauges. Curves were banked for safe turns, just like modern racetracks. Drainage culverts ran beneath roads, preventing washouts that plagued contemporary highways. This uniform design meant a merchant could travel from Britannia to Syria without adjusting to different road conditions. Compare that to today's patchwork of national highway standards, and you'll appreciate Rome's visionary thinking. But here's the twist: these roads were ecological masterpieces too. Locally quarried materials reduced transport emissions, a lesson in sustainability we're relearning with regional concrete plants. The compacted layers acted like sponges, replenishing groundwater instead of creating runoff. Modern permeable pavements, hailed as green innovations, achieve what Roman roads did naturally. Even their maintenance strategy was revolutionary. Rather than waiting for potholes, crews proactively resurfaced sections on rotating schedules, an approach modern cities now call predictive infrastructure management. Perhaps the most telling proof of their brilliance lies beneath London's bustling streets. When archaeologists excavated the Roman road to Silchester, they found its original gravel still intact under medieval and Victorian layers. Centuries of builders had simply paved over the ancient foundation, trusting its integrity more than their own designs. As engineers today grapple with crumbling bridges and overpasses, Rome's roads whisper a timeless truth: infrastructure isn't about how fast you build, but how long it lasts. The next time you hit a pothole, remember, the solution might not lie in futuristic materials, but in the layered wisdom beneath your feet. 2,000 years before bicycle chains spun through modern cities, Chinese engineers of the Han Dynasty were already mastering the silent dance of linked metal. Deep in the heart of ancient foundries and irrigation fields, the first recorded chain drives transformed human effort into mechanical power with startling efficiency. Picture a series of interlocking bronze rings, precisely cast to glide over wooden sprockets, transferring force from water wheels to massive bellows that fed furnaces with a steady blast of air. This wasn't just a labor-saving device, it was the birth of continuous power transmission, a principle that would later propel the Industrial Revolution and shape the modern world. The genius of these early chains lay in their dual purpose. In iron smelting operations, they synchronized the movement of multiple bellows, ensuring constant airflow to maintain blistering temperatures needed for high-quality steel, a technique that wouldn't reappear in Europe until the 18th century. Meanwhile, in sprawling agricultural complexes, chain pumps lifted water from canals to terraced fields with rhythmic precision. Archaeologists have uncovered ceramic models depicting these systems, showing how buckets attached to chains could elevate water over 30 feet without a single pump or piston. What's remarkable is how little the basic design has changed. The roller chains in today's motorcycles and factory equipment operate on nearly identical principles, just with hardened steel instead of bronze. Modern engineers still marvel at the Han Dynasty's solutions to problems we assume are contemporary. Their chains incorporated clever features like tapered links to reduce friction and staggered joints to distribute, where innovations that bicycle manufacturers would patent as new discoveries in the 1800s. The silent efficiency of these ancient drives came from meticulous craftsmanship. Surviving examples show tolerances within 2 millimeters, achieved with nothing but hand tools and calibrated sighting sticks. When Leonardo da Vinci sketched his version of a chain drive centuries later, he was unknowingly recreating what Chinese artisans had already perfected. Perhaps the most profound lesson lies in how these humble components enabled larger technological leaps. The consistent blast from chain-driven bellows allowed hand metallurgists to produce cast iron on an industrial scale, creating tools and weapons that shaped military and economic dominance. Similarly, irrigation chains transformed arid regions into productive farmland, supporting population growth that fueled cultural flourishing. It's no coincidence that chain technology peaked alongside some of China's most brilliant inventions, from the seismograph to papermaking. The relationship was symbiotic. Precision chains enabled advanced machinery, while the demand for better machines drove chain refinement. Today, the legacy of these ancient drives hums all around us. The timing chains in car engines, the conveyor belts in factories, even the cables lifting ski resort gondolas all descend from that Han Dynasty breakthrough. What's poetic is how the original applications still hold wisdom for modern problems. Engineers developing solar-powered irrigation in Africa have adapted ancient chain pump designs for off-grid use, proving their timeless utility. And in robotics labs, researchers study hand chain flexibility to improve mechanical limb movement. The next time you shift gears on a bike, remember, you're not just turning pedals, you're spinning a thread that connects directly to the hands of artisans who, 2 millennia ago, saw the potential in a simple loop of metal links. Their vision reminds us that progress isn't always about disruptive leaps. Sometimes it's the quiet, persistent turning of small innovations that ultimately moves the world forward. Viking navigators staring into the overcast North Atlantic skies held a secret weapon not in their swords or ships, but in their hands. A translucent calcite crystal, now called a sunstone, could reveal the sun's position even when clouds hid it completely. Here's how it worked. By rotating the stone until light passing through it aligned in a specific polarization pattern, sailors could pinpoint the sun's location with eerie accuracy. This wasn't just clever, it was advanced optics centuries before scientists understood light waves. Modern experiments prove the technique's precision. Researchers using replica sunstones on cloudy days consistently located the sun within 5 degrees, a margin tight enough to guide longships across thousands of miles of open ocean. What's astonishing isn't just the tool itself, but how Vikings combined it with nature's cues to create a navigation system rivaling modern instruments. They tracked migrating birds like Arctic terns whose flight paths pointed toward land. They read ocean swells like road signs, recognizing how waves refract around distant islands. At night, they relied on star paths constellations rotating around Polaris long before celestial navigation became formalized. Even whale behavior offered clues. Feeding grounds often meant shallow waters near coastlines. This wasn't just wayfinding, it was an entire philosophy of movement, treating the natural world as a living map. The sunstone's legacy extends far beyond Viking voyages. Its principle of light polarization now underpins technologies from LCD screens to advanced aviation compasses. During World War II, pilots used similar crystals to spot enemy planes through glare, a direct descendant of Viking methods. Today, researchers are revisiting these ancient techniques for space navigation. Without GPS satellites, future Mars explorers might rely on polarized light sensors inspired by sunstones to orient themselves in the planet's dusty atmosphere. The irony, NASA cutting-edge tools could trace their lineage back to a Norse sailor squinting at a cloudy sky with a chunk of calcite. But perhaps the most profound lesson lies in how Viking navigation embraced uncertainty. Where modern GPS gives pinpoint accuracy, their system accepted nature's variability, adjusting to fog, storms, and seasonal shifts with fluid expertise. Archaeologists studying Norse settlement patterns found they often chose landing sites not for straight-line efficiency, but for adaptive advantages like seasonal currents or whale migrations. This wasn't random, it was a masterclass in resilient navigation, where multiple redundancies, sunstones, wildlife, stars created a fail-safe network. As climate change disrupts modern shipping routes with melting ice and stronger storms, maritime experts are studying Viking strategies for navigating unpredictable environments. The rediscovery of sunstones in the 21st century reads like a detective story. For years, scholars dismissed medieval texts mentioning solar crystals as myth until archaeologists found calcite fragments aboard a 16th century shipwreck, perfectly preserved near the captain's quarters. Laboratory tests confirmed their optical properties matched ancient descriptions. Now, museums worldwide display these unassuming stones beside satellite navigation exhibits, bridging past and future. The next time you glance at your phone's GPS, remember, the real revolution in navigation happened 1,000 years ago when a sailor held a crystal to the sky and saw the invisible. In the arid landscapes of Rajasthan, where temperatures soar high enough to evaporate entire lakes, ancient engineers sculpted miracles from stone stepwells like Chand Baori, descending 13 stories into the earth like inverted pyramids of cool sanctuary. These weren't just reservoirs, they were multi-layered masterpieces where every step served dual purposes. The symmetrical staircases, some with over 3,000 steps, did more than guide villagers to water. They maximized surface area to accelerate evaporative cooling, dropping temperatures by 20 degrees at the lowest levels. Imagine the precision, steps spaced to create shade patterns that minimized water loss, while narrow openings at the top reduced dust contamination. This wasn't just storage, it was climate control carved in sandstone. But stepwells transcended engineering. They became the beating hearts of communities, blending utility with artistry in ways modern infrastructure rarely attempts. Pillared pavilions at intervals hosted merchants and travelers, their carved niches doubling as cooling chambers where breezes chilled by the water below circulated naturally. During droughts, these spaces transformed into communal kitchens or makeshift schools, proving adaptability was baked into their design. The ornate frescoes and sculptures lining the walls weren't mere decoration, they told stories of monsoons past, serving as hydrological records for generations. Today's architects marvel at how these structures fulfilled roles we now assign to separate buildings. Water towers, community centers, even art galleries, all woven into one. The science behind their resilience is equally breathtaking. By burying water deep underground, engineers avoided the algae blooms that plague modern open reservoirs. The stepwell's gradual descent allowed silt to settle naturally, purifying water without filters, a technique now emulated in bioswales for urban stormwater management. At Chand Baori, the zigzagging stairs created microclimates. Archaeologists found evidence that herbs planted along certain levels acted as natural disinfectants, their roots filtering impurities. It's a blueprint for sustainable water management that's inspiring solutions from Cape Town to Chennai, where architects are designing stepwell parks that combine rainwater harvesting with public recreation spaces. Modern attempts to replicate these ancient wonders reveal just how advanced they were. When engineers in Jaipur built a stepwell-inspired cooling system for a government building, they discovered the original designs accounted for seasonal wind shifts, something their models had overlooked. The orientation of Chand Baori steps, for instance, aligns with summer breezes to enhance evaporation, while winter angles minimize it. Contemporary projects like the Stepwell project in Gujarat are documenting these nuances, merging traditional knowledge with drone mapping to revive abandoned wells. The results speak volumes. Restored stepwells in drought-prone regions now provide year-round water to villages, their yields outperforming concrete tanks built at 10 times the cost. What's most striking is how these structures honored water's cultural significance. Unlike utilitarian modern dams, stepwells celebrated water through design. Their intricate geometries mirrored the sacred mandala, symbolizing cosmic order. Ritual spaces near the water's edge encouraged conservation through reverence, a psychological nudge modern conservationists are only now rediscovering. As climate change intensifies water scarcity, the stepwell's legacy offers more than engineering lessons. It's a reminder that the most enduring solutions marry function with meaning. When a 17th century farmer descended those steps, he wasn't just collecting water, he was participating in a system that honored every drop as both lifeblood and art. In our rush to innovate, perhaps we've forgotten that the deepest wisdom often lies not in reinvention, but in remembering. In the hands of a 9th century Persian astronomer, a brass disc no larger than a dinner plate held the secrets of the cosmos. The astrolabe, perfected by Islamic scholars during the golden age of science, wasn't just a tool, it was an entire universe distilled into gears and engravings. Picture a handheld planetarium with rotating plates etched with star maps, adjustable for latitude, capable of calculating prayer times, predicting sunrise, or even surveying land. Its front bore a spiderweb-like retere, a rotating star chart with pointers marking key celestial bodies, while its back featured scales for trigonometry and angular measurements. This wasn't just engineering, it was poetry in brass, a device so versatile it made modern GPS look single-minded. The astrolabe's brilliance lay in its interdisciplinary genius. Al-Biruni, one of Islam's greatest polymaths, used it to measure the Earth's circumference with startling accuracy. Navigators from Baghdad to Cordoba relied on its readings to cross deserts and seas, long before compasses reached Europe. But its real innovation was modularity. Swapping out plates for different latitudes allowed one instrument to serve from Scandinavia to the Sahara. Modern apps toggle between functions with a swipe. Astrolabe users achieved similar flexibility by rotating brass components with their thumbs. The parallels to today's technology run deep. Its layered plates foreshadowed graphical user interfaces, while its trigonometric calculations mirrored early analog computers. What's often overlooked is how these devices democratized knowledge. Unlike bulky armillary spheres reserved for elite scholars, astrolabes fit in a traveler's pouch. Surviving manuscripts reveal they were used by farmers determining planting seasons, merchants calculating caravan routes, and architects aligning mosques with Mecca. The Andalusian astronomer Al-Zarqali even crafted a universal astrolabe that worked at any latitude, a feat of inclusivity centuries ahead of its time. This ethos lives on in today's open-source software and affordable scientific tools, proving accessibility has always been key to progress. The craftsmanship behind astrolabes was equally revolutionary. Artisans employed lost wax casting techniques to create gears with teeth precise to fractions of a millimeter, their accuracy rivaling modern CNC machining. Engravers etched scales so finely that a single degree might contain 10 subdivisions comparable to the resolution of early sextants. These weren't just instruments, they were masterclasses in precision engineering. When European monks later struggled to replicate Islamic astrolabes, their clumsy copies revealed how far the technology had leaped ahead. Today, the astrolabe's legacy spins quietly through our world. Its stereographic projection, the method for mapping a sphere onto a flat surface, still teaches astronomy students. The gear trains that powered its moving parts evolved into mechanical clocks, then calculators, then the very computers we use to study these ancient devices. Perhaps most poignantly, modern navigators training for electronic failures still learn astrolabe basics, a 1,000-year-old backup system for the digital age. The next time you check your phone for the time or your position, remember, you're holding the spiritual descendant of a medieval marvel that proved the universe could be held in your palm. The Aztecs faced an impossible challenge: how to feed a booming capital city built on a lake. Their solution: chinampas, floating gardens so productive they yielded up to 7 harvests a year while actually improving the ecosystem. Picture this: rectangular plots woven from reeds and willow branches, anchored to the lakebed with sturdy posts, then piled high with nutrient-rich mud scooped from the lake bottom. These weren't just rafts, they were living, breathing farms where the boundaries between land and water blurred beautifully. Crops like maize, beans, and squash thrived in the fertile muck, their roots drinking directly from the mineral-rich waters below. Meanwhile, the channels between chinampas teemed with fish attracted by the shade and nutrients, creating a symbiotic relationship that modern aquaponics systems strive to replicate. What made these floating farms revolutionary wasn't just their productivity, it was their sustainability. Unlike modern agriculture that strips nutrients from soil, chinampas grew richer over time. Aquatic plants like duckweed and water hyacinth, often considered pests today, were harvested regularly to replenish the garden's fertility. The Aztecs even developed a system of crop rotation using chinampa nurseries, where young plants grew before transplanting to main plots, minimizing soil disturbance. Archaeologists studying sediment cores have found these practices maintained stable phosphorus and nitrogen levels for centuries, something industrial farms struggle to achieve even with synthetic fertilizers. The real stroke of genius lay in how chinampas turned a disadvantage to Tenochtitlan's swampy location into its greatest asset. The surrounding water acted as a natural thermostat, protecting plants from frost and extreme heat. Canal water kept roots hydrated during droughts, while the mass of floating gardens actually stabilized the lake's water levels during floods. Modern floating farms in Bangladesh now employ similar principles to survive monsoon seasons, proving the Aztecs' understanding of hydrological balance was centuries ahead of its time. Even their pest control methods were visionary. Dragonflies attracted to the water kept harmful insects in check, eliminating the need for pesticides that plague contemporary agriculture. Today's urban farmers are rediscovering these ancient secrets with striking results. In Mexico City, the last surviving chinampas of Xochimilco now supply organic produce to high-end restaurants while filtering urban runoff naturally. Similar projects have sprung up in Detroit's vacant lots and Singapore's rooftop gardens, adapting the floating farm concept to modern cities. The most ambitious revival comes from China, where researchers have created high-tech chinampas using biodegradable polymers instead of reeds, boosting yields by 30% while cleaning polluted waterways. The irony: after decades of draining wetlands for farmland, we're finally realizing the Aztecs had it right all along. Sometimes the most productive fields aren't on land at all, but floating in perfect equilibrium with the water that sustains them. Perhaps the deepest lesson lies in how chinampas embodied the Aztec worldview, where modern agriculture often sees nature as an obstacle to conquer. Their floating gardens celebrated interdependence. Farmers considered the lake a living entity, making offerings to its spirits before harvests. This cultural reverence translated into meticulous ecological stewardship, something sorely missing from today's extractive farming models. As climate change forces a reckoning with unsustainable practices, the chinampa whispers an alternative. Abundance doesn't come from dominating nature, but from dancing with its rhythms. The proof floats quietly in history's waters, waiting for us to recognize that the future of farming might just be anchored in the past. Divers exploring a Roman shipwreck near Antikythera in 1901 expected to find statues and pottery, not a corroded bronze lump that would rewrite the history of technology. After decades of study, X-rays revealed the truth. The Antikythera mechanism was an astronomical computer of staggering complexity. Its 37 interlocking bronze gears tracking celestial movements with a precision unmatched for 1400 years. This wasn't just a calendar, it was a miniature cosmos in a box, predicting solar eclipses to the hour and modeling the erratic motions of planets with a sophistication that wouldn't reappear until the clocks of 18th century Europe. The genius of the mechanism lay in its differential gearing, a system thought to have been invented in the 1700s for steam engines. Tiny teeth, some just a millimeter wide, calculated the moon's elliptical orbit using a pin and slot device that accounted for its varying speed. Another gear simulated the 19-year metonic cycle, crucial for aligning lunar and solar calendars. Modern engineers rebuilding the device found its eclipse predictions were accurate to within 2 hours over a 4-year span comparable to early digital computers. What's astonishing isn't just the math encoded in bronze, but the worldview it represents, a universe governed by mechanical laws, graspable through gears and ratchets. But the real mystery is why this technology vanished. Ancient texts hint at similar devices. Cicero wrote of a machine built by Archimedes that reproduced the motions of the heavens. Yet no others survive, their knowledge perhaps lost in the burning of Alexandria's library. The mechanism's rediscovery forces us to confront an uncomfortable truth: technological progress isn't inevitable. Civilizations can peak, decline, and leave fragments so advanced, later generations dismiss them as impossible. Today, the Antikythera mechanism's legacy spins quietly through modern engineering. Its compact gear trains inspired the miniaturized mechanical computers used in World War II torpedoes. Watchmakers like Patek Philippe study its differential systems for ultra-complex timepieces. Even NASA has consulted reconstructions when designing compact orbital calculators for spacecraft. The device's most profound lesson might be its humility, a reminder that innovation isn't linear, that brilliance can flicker out and be reborn centuries later. As we race toward quantum computing, this 2,000-year-old clockwork whispers across time. The future might just be waiting in the past, buried beneath the waves, patiently ticking until we're ready to understand it again. In the heart of 16th century Istanbul, where European cities still dumped waste into open sewers, Ottoman engineers were crafting a water network so advanced it would make modern urban planners pause. The Süleymaniye Mosque complex wasn't just a place of worship, it was a hydraulic masterpiece with water channels so meticulously designed they could rival today's municipal systems. Picture this: pure spring water captured from hills miles away, channeled through a series of underground clay pipes and stone aqueducts, then filtered through layers of sand and charcoal before reaching marble fountains. This wasn't just plumbing, it was a symphony of gravity and craftsmanship, delivering clean water to thousands without a single pump or electrical grid. The Ottomans' secret weapon was their understanding of elevation. By mapping the city's contours with astonishing precision, they created a gravity-fed system where water flowed effortlessly from reservoirs to public taps, even in multi-story buildings. The Süleymaniye's ablution stations, where worshippers performed ritual cleansings, featured constant running fountains with precise water pressure, achieved through carefully calibrated pipe diameters and gradient drops. Modern hydraulic engineers have reverse-engineered these designs, discovering the system could maintain optimal flow rates despite seasonal variations, a feat modern grids often struggle with during peak usage. But the real innovation lay in how these systems married utility with artistry. water didn't just arrive, it danced. Elaborate sesame fountain structures turned functional spigots into architectural jewels. Their calligraphy adorned spouts, transforming every drink of water into a moment of beauty. The Ottomans understood something we often forget. Infrastructure isn't just about function, it's about dignity. When a laborer paused to sip from a fountain, they encountered the same craftsmanship reserved for sultans' palaces. Today's stark, utilitarian water systems could learn from this philosophy, whereas the joy in drinking from a steel pipe protruding from a concrete wall. What's most striking is how these networks reflected Islamic values of public health. While medieval Europe viewed bathing as suspicious, Ottoman hammams and mosque courtyards made cleanliness accessible to all social classes. The Suleimani's water channels extended beyond the mosque, feeding public baths, hospitals, and even street-side drinking fountains for travelers. This wasn't just engineering, it was an entire culture built around communal well-being. Modern epidemiology confirms their wisdom. Cities with Ottoman-style water networks had lower rates of waterborne diseases than their European counterparts well into the 19th century. The legacy of these systems flows quietly through modern Istanbul. Many neighborhoods still rely on restored Ottoman pipes, their terracotta interiors naturally inhibiting bacterial growth, a feature scientists only recently understood. Contemporary architects studying the Suleimani's rainwater harvesting techniques have adapted them for green buildings, using gravity-fed channels to irrigate rooftop gardens. Even the aesthetic lessons resonate. Projects like New York's Waterline Square incorporate ornamental fountains inspired by Ottoman designs, proving that beauty and utility need not be strangers. Perhaps the ultimate testament to their brilliance lies in a simple ritual still practiced today. Before major repairs, modern Turkish plumbers recite a centuries-old prayer for the original engineers, a tradition acknowledging that true mastery transcends time. As climate change strains water resources worldwide, these ancient networks whisper a timely truth. Sustainability isn't just about pipes and pressure. It's about seeing water as sacred, infrastructure as art, and every public tap as a covenant between civilization and the elements that sustain it. Celtic roundhouses weren't just shelters, they were climate control systems carved from earth and straw. Picture a structure with walls woven from hazel branches, packed with clay and dung for insulation, topped by a conical thatch roof so thick it could shrug off winter storms while trapping warmth like a thermal blanket. Tests on reconstructed roundhouses show interior temperatures remained a steady 60 degrees Fahrenheit, even when frost gripped the landscape outside. This wasn't accidental comfort, it was physics mastered through observation. The circular shape eliminated cold corners where heat typically escapes in rectangular buildings, while the central hearth's warmth radiated evenly along the curved walls. Modern passive houses, celebrated for slashing energy use by 90%, employ this same principle, just with triple-paned windows and heat exchangers instead of wattle and daub. What's truly revolutionary is how these homes embraced sustainability at every level. Thatch, often dismissed as primitive, outperforms many modern roofing materials. Its hollow stems create natural air pockets that insulate better than asphalt shingles, while its breathability prevents moisture buildup. Archaeologists analyzing roundhouse floors have found evidence of ingenious floor heating. Layers of heated stones beneath clay flooring radiated warmth for hours after fires burned low. Even the orientation was strategic. Doorways consistently faced southeast across Celtic settlements, capturing morning sunlight for natural heating while avoiding harsh northwestern winds. Today's architects are relearning these lessons. In Scotland, eco-villages like Findhorn build modern roundhouses with hempcrete walls, a material strikingly similar to the ancient mix of straw and lime. proving that Neolithic solutions can meet 21st century energy standards. The portability of these structures offers another masterclass in low-impact living. When soil nutrients depleted or communities needed to relocate, roundhouses could be disassembled without a trace. Their materials, wood, thatch, earth, returned to the ecosystem harmlessly, a stark contrast to today's construction waste, which accounts for 30% of global landfill volume. Contemporary nomadic architecture, from Mongolian yurts to Scandinavian Sami Lavu tents, still echoes this philosophy, but the Celts took it further. Their homes weren't just temporary, they were cyclical. Excavations reveal sites where roundhouses were rebuilt in slightly shifted locations over generations, allowing previously used land to regenerate, a practice modern permaculture calls pulse grazing for human habitats. Perhaps the most urgent lesson lies in roundhouses' social design. The circular layout fostered equality, no hierarchical seating arrangements, no isolated rooms. Families cooked, worked, and slept in a single open space where shared body heat contributed to warmth, and communal living reduced per capita energy needs. Compare this to today's sprawling suburban homes, where empty rooms are heated unused, and isolation has become literal architecture. Projects like Ireland's Clough Jordan Eco-Village are flipping this script, designing clustered round-inspired homes with shared thermal mass walls that cut heating costs by 70% while rebuilding neighborly connections. The ultimate testament to these ancient engineers, their roundhouses worked so well, they persisted for over 2,000 years, outlasting Roman villas with their hypocaust heating, medieval castles with their drafty stone walls, even early modern cottages prone to dampness. As we face housing shortages and climate crises, the roundhouse whispers a radical idea. Maybe the most advanced home isn't the one with the most gadgets, but the one that listens to the land. Its genius wasn't in conquering nature, but in collaborating with it, turning wind, sun, and even cow dung into allies. The next time you adjust your thermostat, remember, the blueprint for comfort might lie not in the future, but in the ashes of a hearth that kept generations warm without a single watt of electricity. Rising like a white heron from the plains of Hyogo, Himeji Castle has withstood over 400 years of earthquakes without a single collapse, not by resisting nature's fury, but by dancing with it. The secret lies in a marriage of flexibility and foresight. Unlike rigid medieval fortresses that crumbled under seismic stress, Japan's wooden castles were engineered to sway. Interlocking joints carved with the precision of fine cabinetry allowed beams to shift and groan during tremors before settling back into place. Modern engineers call this energy dissipation, but 17th century craftsmen knew it simply as smart joinery. The same technique now appears in Tokyo's skyscrapers, where flexible steel frames mimic Himeji's wooden skeleton, proving that sometimes the best defense isn't strength, it's suppleness. Beneath the castle's graceful towers lies another stroke of seismic genius, stone foundations that function like natural shock absorbers. Thousands of irregularly shaped rocks were stacked without mortar, creating a base that could subtly rearrange itself during quakes. When tremors hit, friction between the stones converted destructive energy into harmless movement, much like modern base isolators, those layered rubber and steel pads now installed beneath hospitals and nuclear plants. Archaeologists studying Himeji's foundation after the 1995 Kobe earthquake found the stones had shifted exactly as intended, sparing the delicate wooden superstructure above. It's a stark contrast to modern concrete foundations, which often crack catastrophically under similar stress. What's most remarkable is how these defenses serve dual purposes. The same flexible joints that thwarted earthquakes also made castles harder to burn during sieges. Wooden pegs would char without failing, buying critical time. Sloping stone walls called ishi-atoshi not only deflected tremors but also ricocheting cannonballs. Even the castle's labyrinthine layout, designed to confuse invading armies, inadvertently created seismic buffers by distributing weight unevenly across the complex. This wasn't just engineering, it was holistic design where every element addressed multiple threats simultaneously. Contemporary architects call this multi-hazard resilience, but samurai builders didn't need jargon. They had survival instincts honed by centuries of disasters. The proof of their mastery lies in the timeline. While modern buildings in Kobe pancaked during that 1995 quake, Himeji emerged with just minor plaster cracks. Nearby Osaka Castle, a 20th century concrete replica of traditional design, required extensive repairs, an irony not lost on engineers. Today, researchers pore over Edo period carpentry manuals, discovering that what they assumed were decorative flourishes actually served calculated structural roles. The curved eaves that give Japanese castles their distinctive silhouette, for instance, aren't just aesthetic, they redistribute wind and seismic loads away from critical supports. Nowhere is this ancient wisdom more urgently relevant than in today's disaster-prone cities. From San Francisco to Istanbul, engineers are blending Himeji's principles with cutting-edge materials. A skyscraper in Taipei uses tuned mass dampers inspired by castle roof ornaments to counteract sway. Base isolators beneath Christchurch's new hospital incorporate crushed stone layers mimicking Himeji's foundation. Even temporary housing designs in Nepal now feature interlocking wooden joints adapted from samurai blueprints, proving that resilience doesn't require high-tech solutions, just timeless intelligence. Perhaps the deepest lesson lies in the philosophy behind these castles. Where modern engineering often seeks to dominate nature, Himeji's builders worked with it, recognizing that flexibility and adaptation trump brute force. As climate change intensifies storms and quakes, their approach feels less like history and more like prophecy. The next time you see a shock-absorbing high-rise or a base-isolated bridge, remember, the future of disaster-proof design might just be standing in the shadow of a 400-year-old wooden tower, whispering secrets on the wind. Cleopatra's iconic winged eyeliner wasn't just a symbol of beauty, it was a stealthy defense system. Those dramatic kohl-rimmed eyes, immortalized in ancient art, contained a secret ingredient: lead salts. Modern scientists once dismissed this as a hazardous choice, but recent discoveries reveal the opposite. At France's Louvre Museum, researchers analyzed Egyptian cosmetics using synchrotron radiation, a high-tech X-ray technique. They found that the lead compounds in kohl triggered biochemical reactions that boosted nitric oxide production in skin cells by up to 240%. This isn't just chemistry, it's microbiology at work. Nitric oxide acts as the immune system's alarm bell, rallying white blood cells to fight bacteria like a microscopic militia. Along the Nile's marshy banks, where eye infections ran rampant, kohl became an accidental antibiotic, protecting wearers from trachoma and other blinding diseases. The deeper brilliance lies in how Egyptians refined their formulas. Excavated cosmetic palettes from the Old Kingdom show evolving recipes. Early versions used raw galena, while later mixtures combined lead salts with crushed pearls and almond oil for smoother application. This wasn't trial and error, it was systematic optimization. Papyrus medical texts like the Ebers Papyrus describe precise kohl preparations for different ailments, proving they recognized its therapeutic effects. Fast forward to today, and researchers at the University of Pisa are testing synthetic versions of these lead compounds as potential treatments for antibiotic-resistant infections. The irony, while modern medicine races to combat superbugs, ancient apothecaries may have left us a blueprint in their makeup jars. What's often overlooked is how Egyptian cosmetics blurred the line between pharmacy and vanity. Their green eyeshadows made from malachite contained copper, a known antimicrobial now used in hospital bed rails to prevent bacterial growth. Henna tattoos weren't just decorative, their lawsone molecules protected against fungal infections common in hot climates. Even their perfumed oils, infused with myrrh and cinnamon, doubled as preservatives and wound disinfectants. This holistic approach foreshadowed today's cosmeceutical boom, where moisturizers contain retinol and sunscreens pack antioxidants. The difference, where we separate beauty counters from drugstore aisles, Egyptians saw them as one and the same. The most profound lesson emerges from how these discoveries challenge modern assumptions. For decades, archaeologists assumed ancient makeup's lead content proved ignorance of toxicity, but new evidence suggests Egyptians might have understood dosing intuitively. By keeping kohl external and avoiding ingestion, they harnessed lead's benefits while minimizing risks, a precursor to modern topical medications. In labs from Cambridge to Cairo, scientists now explore whether other vilified ancient ingredients, like mercury-based vermilion or arsenic sulfides, might hold similar hidden potentials when used correctly. Perhaps the ultimate testament to their legacy lies not in petri dishes, but in cultural continuity. Bedouin tribes still craft kohl from soot and olive oil for eye protection, while Ayurvedic kajal remains a staple across South Asia. Modern makeup brands, from luxury lines to indie startups, increasingly infuse products with probiotics and prebiotics to support skin microbiomes, a concept the Egyptians pioneered millennia ago. The next time you swipe on eyeliner, remember, you're not just accenting your eyes. You're participating in a tradition where beauty and biology have always been intertwined, where the flick of a brush carries echoes of a civilization that understood science's most enduring truth. Sometimes the most revolutionary solutions aren't found in labs, but in the everyday rituals of those who came before us. Between the Tigris and Euphrates rivers, where scorching sun could evaporate an entire season's rain in weeks, Mesopotamian engineers performed what seemed impossible. They turned desert into breadbasket. Their secret, a spiderweb of canals so precisely engineered, they transformed barren plains into the world's first agricultural empire. Picture workers digging trenches with copper tools, their paths following the land's natural contours to harness gravity's pull. These weren't just ditches, they were hydrological masterpieces, with silt traps to prevent clogging and adjustable gates to regulate flow. Modern satellite imagery still reveals their ghostly outlines beneath Iraq's sands, tracing patterns that fed cities like Ur and Babylon for millennia. What set these systems apart was their dual relationship with water. They didn't just distribute it, they tamed it. During spring floods, diversion canals siphoned off excess water into reservoir basins, preventing catastrophic overflows while storing precious reserves for dry months. Levees reinforced with woven reeds and bitumen, and ancient asphalt held firm against torrents that would wash away modern earthen berms. Archaeologists have uncovered clay tablets detailing maintenance rosters, proving these were no ad hoc projects but carefully managed public works. One tablet from Lagash records a canal inspector's report noting 32 cubits cleared of silt, with the efficiency of a modern municipal logbook. The real stroke of genius lay in how these networks sculpted society itself. Maintaining miles of waterways required cooperation across villages, birthing history's first administrative bureaucracies. Temple officials allocated water rights based on field size, an early form of resource equity, while courts settled disputes over dam breaches. This collective effort became the foundation of urban life, reliable harvests meant not everyone had to farm, allowing specialized roles like scribes, potters, and metalworkers to emerge. The invention of writing itself traces back to tracking grain stores and irrigation labor. In essence, the canals didn't just water crops, they cultivated civilization. Today's engineers are rediscovering Mesopotamia's wisdom as climate change strains modern water systems. In Arizona's Salt River Valley, farmers have adopted ancient surge flooding techniques where controlled bursts of water reduce seepage losses by up to 20%. Dutch water managers study Babylonian levee designs to reinforce their flood defenses, noting how alternating layers of reed mats and soil created flexible barriers. Even the concept of spate irrigation, using seasonal floods to fertilize fields, is being revived in Ethiopia's drought-prone regions with striking success. The irony, after centuries of concrete megadams and diesel pumps, we're circling back to techniques refined 4,000 years ago. Perhaps the most poignant lesson lies in the system's decline. When empires collapsed and maintenance lapsed, canals silted up, returning fertile lands to dust. Modern satellite images show this reversal starkly. Once green fields, now cracked and barren beside the ghostly traces of forgotten waterways. It's a warning etched in mud bricks: no engineering, no matter how brilliant, outlasts the society that sustains it. As California's Central Valley sinks from overpumping and the Colorado River dwindles, Mesopotamia's legacy whispers across millennia. True abundance flows not from controlling nature, but from dancing with its rhythms, generation after generation. The original engineers of the Fertile Crescent didn't just move water, they moved humanity forward, one carefully channeled drop at